So, moving on to different technology, it's now about thermal energy storage systems, and I'd like to present a study that we performed a couple of years ago in the framework of the International Energy Agency technology collaboration platform on energy storage. So, we called it a simple tool for the economic evaluation of thermal energy storage systems. So here to start with, you see two different thermal energy storage systems. On the left, it's a large pit thermal energy storage in Denmark, and on the right, it's a small a small sorption thermal energy storage as part of the big water. Both systems are in operation, and you see there's quite a difference in costs. So you see on the left, the pit storage. Here we have a cost of 0.4 euro per kilowatt hour installed storage capacity. And on the right, it's in the order of 100 euro per kilowatt hour storage capacity installed. And well, this was, or this can be a starting point to discuss about how to assess the storage capacity costs of these systems and how to assess their economic viability, because both systems are successfully in operation. So our assumption for this analysis was that energy storage is economically if the costs of energy supplied by the storage are below the costs of energy from the market, as Jan mentioned in the introduction. Otherwise, you will not invest in energy storage. And translating this on an annual basis means that the annual payment for the energy storage investment should be below the annual savings of reference energy costs. And this, let's say, this requirement will be now used to develop the evaluation method. So we have two, let's say, tools, two approaches to look at thermal energy storage economics. And the first, the so-called top-down approach, we look at the acceptable storage capacity costs. We will see these depend on the market, on the user expectations. And the second approach, it's the other way around, so-called bottom-up approach. Here we calculate the realized storage capacity costs of existing thermal energy storage systems. And of course, these storage is economical if the acceptable are higher than the realized costs. So this work has been published already back in 2015. Here you see the corresponding papers if you would like to have a closer look afterwards. So starting with the top-down approach. First, we have to calculate the annuity factor of the storage investment, because as I mentioned, we want to look at it on an annual basis. So the annuity factor times the investment costs is then equal to the annual payment for the storage investment. And the annuity factor calculated according to this standard formula depends on the interest rate and the payback period. And these two parameters, of course, highly depend on the type of user and their, let's say, their economic backgrounds. So in industry, the interest rate could be something like 10%, and the payback period is, let's say, below 5 years. Then in the building sector, we have a, let's say, moderate interest rate of 5% and longer payback periods of 15 to 20 years that can be accepted. And let's say to show the limits of this evaluation, we defined a third user class called enthusiast, accepting very low interest rates and long payback periods. So again, the assumption is that the annual payment for the storage investment has to be equal than the annual savings. And this can be translated in this formula. So we have the storage capacity costs multiplied with the annuity factor. This is the annual payment for the investment. And this equals the product of reference energy costs. So this is the let's say, the alternative heat or cold supply, multiplied with the annual number of storage cycles. So that would be the, let's say, the energy turnover on a yearly basis. So with this, we get an expression for the storage capacity costs, the acceptable storage capacity costs shown here. Now, I already talked about the annuity factor. We also defined some ranges for the reference energy costs of competing technologies. The values shown here, well, they are not up to date. They reflect the situation back in 2015. So, for example, in industry, back then we had a gas price of between 20 and 40 euro per megawatt hours. Of course, this has been increased recently, but we'll see the overall tool and also the main findings are still valid, even if the reference energy costs need to be adopted. Now to evaluate the storage capacity costs, we choose to plot the storage capacity costs as a function of the annual number of storage cycles. So the number of complete charging, discharging the energy storage system. And in this graph, you see on the left side the range of long-term storage. So up, let's say, between 1 to 10 cycles per year, which one would be ideal, or I'd say is a strictly defined seasonal energy storage system. And on the right-hand side, that's the region of short-term storage. Maybe we have a daily charging, discharging process, or even higher number of cycles per year. And of course, what is obvious, but what is really an important point, is that the acceptable costs of long-term storage are are far below the acceptable costs of short-term storage. So you see, for long-term storage, we have a range of, let's say, 0.1 to 567 euro per kilowatt hours. And in the range of short-term storage, this is increased to something like 100 to several hundreds of euro per installed kilowatt hour. The second approach, so the other way around, we call the bottom-up approach, looks at the realized storage capacity costs, and they are simply the investment costs divided by the installed storage capacity. So the investment costs, they can either be a sum of all the material that is used to build the storage, so the thermal storage material itself, the container, reactor, let's say some heat exchangers, whatever is needed to operate the thermal storage. In some cases, the investment costs are also given as list prices by the manufacturers. And then you have the installed storage capacity in nominal conditions. So, and now interesting is, of course, to bring both together. So top-down and bottom-up approach. And how is this done? Again, we plot the storage capacity costs as a function of the annual storage cycles. So you already saw one of these diagrams where you have these economic viability limits. So that's the limit of acceptable costs. And then you have the realized systems here shown as a blue dot, and either the realized costs are below the acceptable limit, then the system would be economical, or it's the other way around. The costs are above the limit, and then with the given conditions, the system is not economically viable. So now showing some of the results of our study back in 2015. So we grouped the investigated thermal storage systems according to their intended, let's say, application area, and also to the intended user type. First, you see here some examples of long-term thermal storage for building applications. So long-term means we are in the range of 1 to 10 cycles per year. You see several seasonal thermal energy storage systems with 1 to 2 cycles per year. And rather different costs and also at different technology readiness levels, TRL. I don't want to read the table. You can either find it in one of the papers, also with some explanations, or you will have the chance to look at it again in the recordings. I like to highlight the approach by giving an example. By giving actually two examples. So the first one is the seasonal storage of solar heat in Germany, Altenkirchen. You see a sketch of the system and also a picture during construction. So this is a combination of water storage surrounded by ground horse heat exchangers. The idea is that the thermal losses of the water storage are taken up by the ground horse heat exchangers, and doing so, um, uh, there is no need to have a thermal insulation around the central water storage. So you see down the specifications of the system. It's around 7,000 cubic meters of water equivalent, operated in a temperature range between 10 and 90 degrees C. And then you see numbers for the investment costs, INC, and the storage capacity. And as a result, we achieve realized storage capacity costs of 0.5 euro per kilowatt hour. So this would be the bottom-up approach, realized cost of 0.5 euro per kilowatt hours installed capacity. And now what is acceptable in this case? So as a reference energy, we considered district heating back then with costs of 0.08 euro per kilowatt hours. Well, today that would be in the range of, let's say, maybe 10 to 12 cents per kilowatt hour. The user class is definitely the building sector, and this system is operated for 1.7 cycles per year. As a result of this, the acceptable storage capacity costs are in a range of 1.4 to 2 euro per kilowatt hour installed. And with this simple tool, you can say that, yeah, looking at these numbers, the storage can be operated economically viable. So I I choose the word, or I said the word operated. Well, let's see if someone asks it later. If not, I just tell it now. So what is not included in this approach are any OPEX, so any operating costs. This is really, let's say, um, first rough estimate the system just based on looking at the investment costs is economically or not. So it will be more difficult, or it will be worse in reality. A second example, just to show the pictures. So that's really a very large thermal energy storage in Denmark. Just to also show the numbers, it has a storage capacity, thermal storage capacity of 7 gigawatt hours, this single storage, and storage capacity costs of only 0.4 euro per kilowatt hour installed capacity. So the next group, now going to the short-term energy storage applications, and here for the industrial environment. Again, we evaluated several examples, and I'd like to show two of them. First one, it's a dual media storage for waste heat recovery and foundry. Dual media means that we use thermal oil and stones as thermal energy storage medium. And here, see on the left side, the location in the foundry. This storage is intended to be operated for about 200 cycles per year, and the realized costs are around 62 euro per kilowatt hours capacity. So, but given the higher number of cycles per year, such a system can also allow for higher costs than the seasonal systems we have seen before. Second example for short-term industrial storage, it's a project of our institute, mobile sorption heat storage for waste heat recovery. So you see pictures of the truck in operation that takes up a waste heat of a of a waste heat of a waste incineration plant and delivers this to an industrial drying process. A distance of around 7 to 10 kilometers, operated for around 240 cycles per year. And then we achieve realized storage capacity costs of 48 euros kilowatt hour. So back in 2015, this system was not economical, but nowadays the let's say the project team looks again at the results, given the higher gas prices that we currently have. So the last group, short-term systems for building applications. Again, a long list of systems, many of them provided by the participants of this International Energy Agency working group. So many systems at a comparably low TRL at this time. Again, two examples so that you have an idea what is being developed here. First one is the low temperature latent heat storage based on salt hydrates. Low temperature means that it's operated around the melting temperature of 29 degrees C of this salt hydrate, and you see some further specifications regarding storage volume and capacity, and some more pictures of the construction and the operation where you see the solidifying salt hydrate around the heat exchanger. So this system is operated for 200 cycles per year with the indicated storage capacity costs of around 57 to 76 euro kilowatt hour. And the second example, already shown briefly in the introductory slide, the dishwasher with the sorption storage to have an efficient drying process. Also a development of ZA Bayern, where we started with the thermodynamics and finally contributed to the commercial product shown on the pictures. It's, let's say, operated as typical for a dishwasher, maybe for 250 cycles per year, and the costs are in the range of 100 euro per kilowatt hours. And well, that's to show that the more cycles the storage is operated, the higher the acceptable and realized storage capacity costs can be or will be. So to summarize, this rather simple tool to evaluate the economics of thermal energy storages combines these two top-down and bottom-up approaches, following the basic assumption that the annual payment for the storage investment has to be lower than the annual savings of reference energy costs. We have seen that the most influencing parameter is the annual number of storage cycles. That means short-term storage allows for higher costs than long-term storage. And well, applications that offer a high number of annual storage cycles, there you will have the choice of several thermal storage technologies that can become economical. And of course, the systems then have to be compared regarding their physical and technical attributes. As my colleague Jan mentioned in the introduction, there's this new working group on energy storage economics called ECO-ENESTO. It's task 41 of the energy storage TCP of the IEA. It's led by the German Energy Storage Systems Association, BVES. If you're interested, you can contact me or have a look at the indicated website here. Just in brief, what it's about. So the work is organized in 4 different subgroups. Subtasks are they called. One thing is to collect, to identify methods that can be used to evaluate energy storage economics, and here all types of energy storage, so not only thermal but also storage of electricity or chemical energy storage are included. And a second subtask, the top-down, bottom-up approach that I presented to you today, will be further developed and extended to other energy storage technologies. And then one subtask will collect both success stories and what we call difficult cases without business cases of energy storage systems. And the fourth objective will be to develop an energy storage valuation framework. And this will be pretty much about how to identify and monetize benefits energy storage systems can provide. And then in a second step, how to stack revenues from different stakeholders. Yeah, to achieve, let's say, the economical viability of a energy storage technology. So with this last slide, I'd like to thanks for your attention and open for questions.
Yeah, the first question has already been asked in the chat. You may have seen it. What's the more accurate or maybe official definition of short and long-term storage categorization in terms of hours? So, what would you call short-term or long-term?
Well, I think everybody has a different view on what is short and long term. In the last years, we also hear the term medium duration energy storage. We also have a task in the energy storage TCP, and that would be something longer than 4 hours, which is maybe out of the comfort zone of some battery electrochemical energy storage types, but less than seasonal in the terms of storing energy from summer to winter. So I don't know about an official definition. Maybe there are several official definitions of the
Yeah,
yeah,
we
different
have
players.
one in the chat
So
actually of Geoffroy Gauthier,
okay,
who has been speaking here as well.
yeah,
He goes below or above 10 hours, but
yeah,
yeah,
10 hours.
I think what you said is quite true. It's just kind of depends on where it is, what's
Yeah,
the
yeah.
application and so on. But yeah, I think that's rough estimate, but I don't think there's anything official. I'm answering questions I have no idea about. I'm just realizing that. Any other questions? Anything else? Anyone? Yeah, agrees with your answer. I see someone raising their hand. It's HM. Please go ahead, whoever you are.
Yeah, it's me, Harald Milling.
Hi.
Hi.
I have a question. I know I asked to Christoph some time ago, but I forgot the answer. But it's crucial. I remember from the early discussions on the economics of thermal energy storage that was about seasonal, where we calculated the cost of the storage compared to the energy cost delivered, and assuming that the cost of the energy that is stored in the storage is free. It's waste heat. And the background was basically to see if seasonal storage with PCM is feasible at all or not. And when you gave your presentation, there was something that confused me. I thought from reading the papers that in your comparison, you compare either the energy cost if you take it from the grid or whatever it comes from without the storage, and you compare that with you using the storage, but taking the energy that charges the storage for free. And then later you had the cost of I think 6 cents per kilowatt hour from the district heating grid. So I was not sure if now you have taken the cost of the energy for the storage charging into account or not. Can you explain that again?
Good question. An important question, important aspect. No, again, or still the same situation. The costs of to charge the storage are not included. So it's assumed that this is free. No? So even we know that even waste heat is not for free. So, but again, it should be actually a best case assessment. So, because we don't include operating costs, we don't include costs to charge the storage. And yeah, you're right regarding the seasonal energy storage. At least looking at the systems that we evaluated, I would say it's only economically interesting when you have water storage with the size, let's say above several thousand cubic meters. So not a single water storage, or not a water storage in a single house, but at least a small district heating network. So that is at least what we found out. So we haven't had an example of PCM or a thermochemical energy storage that would be economically for really seasonal storage with one cycle per year.
But one more question. Okay, now I understand the background, but we talked about it in before. I am working on a completely different approach, and I compare different storage options. And what I think is important is that in the calculation that you do, you still have as the reference case the assumption that you still get in the future the heating from gas prices or whatever, which can change a lot. Are you working on that? Because I think in the next, I mean, we already saw it in the last 2 or 3 years, but in 10 years the prices are different.
Yes, of course. So we work on, let's say, we still work on this approach. For example, in the new task mentioned in the last slides. So, and you're right, the reference cost shown on the figures corresponded to, especially in the industry class, corresponded to the price of natural gas back in 2015. But the basic approach to have some reference energy costs that the storage has to compete with, this can be again taken as it is. So it's just the question, what are the reference energy costs? So maybe on the long term, the costs of hydrogen imported, as we saw in the first presentation. So that could also be, let's say, a long-term reference energy cost to compete with. No.
Thank you.
Yeah, welcome.
All right. With this, I see no further questions until now. Does anyone still have any? Because if no one does, I think that's I still see someone.
Sorry, me again.
Yeah,
a quick one for the close. We are, as Trenel, we are municipal or public utilities joint venture. We look very much at the heat transition in the local small utility companies, what they can do. And so from today, I learned the heat storage, when you would include the heat generation in summer or the charging of the storage system and discharging, would you rather look at hydrogen for the heat generation in winter, or so? How is that? Is that a clear case already that you say storing summer heat in seasonal storage will beat hydrogen, or what's your take?
Well, maybe first of all, the cost numbers I showed are really euro per kilowatt hour installed, not delivered. So it's not to mix it up with the levelized cost of heat, for example. And the situation today is that, well, especially in Denmark, well, they have very favorable conditions to do so. These large pit thermal energy storages are in operation, and for example, as also mentioned in the chat, they are not operated for strictly one cycle per year. Usually, you have something like 1 to 5. And those very large thermal energy storages are now also being put in operation in other European countries, Germany, Austria. They are talking about having it in Switzerland as well. Well, not that favorable site conditions like in Denmark, but I would say that for large district heating networks, seasonal thermal energy storage based on hot water is definitely an option. Yeah. But I'm not an expert in what is the price of green hydrogen in 2030, 2040, and what really are
we just learned 20 cents.
Barrier
it just
to,
said
yeah,
170
yeah.
to 220 euros per megawatt hours. That's 20 cents.
20 cents.
So I could be
that's a
very
limit
interested
to compete with.
To follow up your work when you feel ready to make statements about levelized cost of heat, including the storage and the charging and the operation, because it's a very interesting work for the huge task of energy transition, and we would be a multiplier and look closely at your results, what it can be. I'd be happy to construct seasonal energy storage in every mid-sized city in Germany. So thank you very much for your work. And
thank you. Let's stay in touch on that. Okay.
That'd be please do so. Thank you for the minute.
Right. We also have another answer for that in the chat. That is Geoffroy Gauthier again. Nice to hear from you. Who basically thinks that storage is mostly a better choice for this than hydrogen, which we'll see about this.
Yes, but I mean, as a scientist who simulates systems, I fully agree. But when you change to the reality of heating an old city that is under restricted construction law, because this is historic cities, you cannot put them in big insulation. I totally agree with you, but this is a view that my scientist half of me says, how stupid can hydrogen for heat be? And then there is the real restrictions from everyday life in a utility, and that matching these two will be interesting. And I'm happy to follow up on your results. And as I say, we built many heat storages if you are right.
Yep. All right. So I think that's kind of a nice finish for this, because we're actually over time anyway. So all I'm going to do now is show you this slide, which is just an ad for the next seminar, which is that one, on the 23rd of November, which will be part 2 of economic considerations in energy storage, this time with Oliver Schmidt of Imperial College London and Matthias Leuthold of Trianel. You may switch that on if you like to. My colleague Stephanie Tafelmeier will be back to host this, and apart from that, I'm finished for today. We're over our time. Have a nice day, people. Have a nice day.